Here's some information about smartphones and accelerometers. I've got a accelerometer app called FiFox or FiFox running here. It's a free sciencey sensing kind of app. It's kind of fun. So on most smartphones, the x-axis is left to right. On the y-axis is up and down on the phone, and the z-axis is into and out of the phone's surface. But you don't actually need to know that for the project, because all that matters is which axis the interesting movement is happening in. I'll show that in a sec, but just notice here, this is feeling basically 0 acceleration meters per second squared in the left-right fashion, close to 0 in the up to down on the phone fashion, and close to 9.7, 9.8 meters per second squared in the z direction, because right now this phone is flat on the surface of a table basically. So it's feeling all the pull in the z direction right now. If I move it to be vertical, the way you would usually hold a phone like that, then you can see it's still feeling basically 0 in the x direction. It's feeling the full pull of gravity in the y direction now, up and down the way you would scroll on the phone, and close to 0 in the z direction. The reason that's not 0 is I must be holding it slightly tilted like this or like that, and so some of that gravity is getting translated into is getting pulled on the z direction. So depending on how I hold it, I can get it closer to 0 or not quite 0. So when you put a cell phone down, let's say on the floor of an elevator, hoping to record things, the orientation that you put it in will determine which axis it feels the movement of the elevator in. And if it's not down completely flat on the floor, like if there's a pebble holding it up, or if the floor of the elevator isn't completely flat relative to the earth, then you're going to get a little bit of non-zero acceleration even in the axes that aren't doing the main movement. Let me show if I turn it sideways here, kind of landscape mode. Now it's feeling all the gravity in the x direction, which is still what would be left and right if I had the phone in portrait mode. There's also this absolute acceleration, which is the square root of the squares of these three things added up. So if you square each one, add them up, take the square root, that's what's called the absolute acceleration, but you don't need to know that for the project we're doing. So why do phones not filter out the effect of gravity? Why do they have it kind of contaminating the data, right? This is not really accelerating in any particular direction, but it looks like it's accelerating with gravity. The reason is that phones have an accelerometer for mainly for the purpose of figuring out which way you're holding them, so it can decide whether to switch from portrait to landscape, for example. Or vice versa. So if the sensor filtered out the force of gravity, then the phone couldn't tell whether it was in portrait or landscape mode. So that's why they have them, and why they don't filter out gravity. Let's switch to a graph here. Let me stop this and junk the data so far and start again so we can see. So here you can see the y values, the blue curve is near 10, it's like 9.8-ish, and the x and z axes are giving me near 0 acceleration because the phone is vertical. Where if I, and here if I moved it left and right, you see how we got a blip in the x direction because I was moving it left and right. If I moved it up and down, we would get a blip in the y direction. You can see how we got a lot of movement in the y direction, the blue curve here, but not much in the x and z. So you have to look at the data given about the elevator movement and see which of the axes is showing just kind of boring, not much happening, and which axis is showing a lot of interesting stuff happening. Another thing to think about for the project, you might have noticed, so we said like if I'm not holding it straight up and down, I'm going to get a value here that isn't exactly 0 or even hovering around 0, like that. So that's related to calibration. Another thing is, how do I know how much margin of error there is? And for that, something that's good to think about is positive controls and negative controls in lab sciences like chemistry or biology. So if a chemist wants to know how accurate their measuring equipment is at detecting pollution, let's say, they would, I guess we can stop this. They would run a sample of like clean water through their measuring equipment, and hopefully their measuring equipment would say that it has zero pollution, but it might actually still have some kind of positive readings. And so if they took some measurement of those, or some kind of characterization of those readings, that would tell them how much measurement error there is in the readings when they actually do have contaminants there. They could also, that would be a negative control, running pure clean water through the instrument. They could also do a positive control where they put a known amount of pollutant into a bunch of clean water, run that through their sample, through their machine where they know what the concentration should be, and then see what the machine says, and then how far off the machine is from what they know the answer should have been is something telling them about their measurement error. So in the project, it's possible to do a negative or positive control, maybe just one of those, by thinking about, is there anything going on where I know what the answer should be, and see how far off things end up from that.